Hello dear students, my name is Suraj Prasad and I am here, Sri Chaitanya Chemistry Senior Lecturer at Gosala campus. Today we will be learning about chemical equilibrium. My today's lecture is about to learn a bit the meaning of equilibrium, chemical equilibrium. Today I will be not doing any numerical kind of stuff. It is a theoretical session. In my next session, we will be doing the numericals. So, in this session, we will try to understand that what is the meaning of chemical equilibrium, because many students, they do not understand it. They directly keep on doing the questions and then they stuck in between when the equilibrium constant on reaction quotient, it comes in the picture. So, first of all, let's try to understand chemical equilibrium, what it is, and the graphs I will definitely mention because that is a part of it. But regarding the other topics, we will be having another session on this. So here we go, chemical equilibrium. As you can see, it is a balance beam, it is balancing the A, B, C, D sides and all. So that is what we will be learning by some skeletal reactions like A plus B gives C plus D, and then we will try to further know the meaning of equilibrium constant. So first of all, let's try to understand the equilibrium, right? Equilibrium, meaning as a general, and then I will come up with the meaning of a chemical equilibrium. So, can you see here, this is a escalator going in the downwards position, and this is a person going in upward direction. Okay. So, escalator going in the downward position and person going in the upward position in the same escalator. Have you even tried it? So, what will happen if the speed at which the escalator which is coming down is the same as the speed of this person moving? If this will be happening, then there will be no change in its position. There will be no change in its position. Like if you have ever tried in the malls or somewhere, okay, and if you have tried the reverse way, you could have succeeded if you have a speed more than the escalator speed, right? Otherwise, what will happen that you will be like him only. So, what I am trying to tell you that this is the equilibrium state, like the position is not getting disturbed, the position is fixed, right? It is like if the speed is same, then only we will say the position is fixed. Obviously, if the person's speed is more, he will cross this escalator. If the escalator speed is more, then definitely this person will be somewhere at the bottom, ground level. So it is like if the speed of this person moving up and lift escalator going down is same, then we will say that equilibrium it exists. Similar thing happens in chemical equilibrium, where instead of these physical examples, we are dealing with the chemical reactions. And in the chemical reactions, it is like about the reactants and products rates, speed. So we'll discuss it, but I hope this example of equilibrium state is clear to you. This type of equilibrium will try to correlate in the chemistry also, chemical reactions also. And this is, I hope, clear. Next. So first let's see the definition of the chemical equilibrium, how it is defined. So chemical equilibrium is a state in which both the reactants and the products are present. Please remember, both the reactants and products, very, very important. Generally in a normal chemical reaction, when we say, which is a unidirectional reaction, we only have more content of the product when the reactants is completely getting used, okay, like that way. So when reactant and product, they both are present, which means this is not a normal irreversible reaction. This, it is talking about the reversible reaction. So first of all, chemical equilibrium, it will exist in the reversible chemical reaction and not in the irreversible reactions. That is the first point. So it is the state in which both the reactants and product are present in concentration which have no further tendency to change with time. Just like that person location was not changing, the concentration of the reactant and products also will not change with time. and so there is no observable change in the properties of the system. So obviously if there is no change in the concentration, the properties, many properties which depends upon the concentration, there won't be any further change. Then second point, this state, it results, so when it will occur, like the example which I just showed you, in that example the speed of the person going up and the escalator going down, the speeds were same, that is how it was happening. So here when it is resulting, it is resulting when the forward reaction proceeds at the same rate as the reverse reaction. Reverse reaction is also called as backward reaction. So like when I say reactants converting into products in a reversible way, then this R to P direction is called as the forward direction reaction, and the P to R is called the backward reaction, so backward direction reaction. So when these rates, when this speed of a forward reaction and the backward reaction, they are same, then only this kind of situation can happen, that concentration will not change, and they will try to get some equilibrium point. The reaction rates, yes, it is given here in the third point, of the forward and the backward reactions are generally not zero, but they are equal. Obviously they should not be zero because reaction has to go on, right? So there should be some speed. Reaction rate here means speed only. So there should be some speed, so they are not zero but they are equal. That is how it is possible to get the equilibrium state. Then there are no net changes in the concentration of the reactants and the products, which we have already seen that there will be something constant. So what is constant? Concentration. Similarly, when we are talking with respect to the gaseous reactants or the products, then there we will see that we can also talk about the constant pressures kind of thing, okay, and for that the different equilibrium constants will also be defined, Kp. So if it is a gaseous media, then we can talk of the Kp also, where we have the gas pressures coming into the picture. Such a state is called what? Dynamic equilibrium. We will talk about it, that why it is called dynamic equilibrium, okay. So in the further slides we will talk about it, what is called dynamic equilibrium. So chemical equilibrium, please remember that it will happen only in the reversible reaction. Now here is something, a diagram for you. Can you see the reaction? I think it is coming completely in your board, right? So A2 plus B2, it is a reversible sign, okay. It is a reversible sign, gives 2AB. This is a balanced chemical reversible reaction, and as you can see that A2 molecules and B2 molecules, they are combining to give the AB molecules, and also AB molecules, they are also combining to give back the A2 and the B2, means they are dissociating, you can say, not combining, we will say that they are dissociating by taking some of the heat or energy, and they are giving back their reactants, which is A2 plus B2. So this type of reaction is actually called as the reversible reaction, okay, where we have both reactions going on, reactant converting to the products and products converting to the reactants. This is called reversible reaction, which is happening over here. I hope you can well see it. A2 plus B2 is getting combined to form AB, and from here AB is getting dissociated and giving A2 and the B2 as a reversible reaction. Now again in this also, like it is a skeletal example, so in this also what we will say, when the rate of the forward reaction and backward will be equal, then the concentrations of A2, B2 and AB, they will become a constant. So constant concentration should come. This is a very important point. Students generally they get confused that whether it is the like rate only or the concentration also. So let me tell you, concentration has to be constant. It is not the case that concentration will be equal, okay. It may equal also, but it is not a special, it is not a like hard and fast rule that the concentration will be equal, but a rate has to be equal. Rate of forward reaction should be equal to the rate of backward reaction. For rate we should not confuse, okay, but for concentration equality is not the condition. For concentration the condition is that their concentration should be constant at a particular, after a particular time interval, where when equilibrium will start exerting, then existing, then at that point we will say concentration has become constant. So this is what we have to understand. Then coming to the important graphs, students. So when we solve the questions, many times in the theoretical questions we will be encountering graphs. Okay, as I told you, today's session is not about solving the numericals. Today's session is about getting the idea of chemical equilibrium. So I will be telling you that how the equilibrium exists, or what is the meaning of it in a chemical reaction. So we have to, obviously, a bit mathematical stuff is important in here in the theoretical part, that is about the graphs. So what was the important point of the chemical equilibrium? I told you just before 2 points, that rate has to be equal and concentration has to be constant after a certain time interval, which is called the TEQ, equilibrium time. So it is like, this is your rate versus time graph, okay, rate on the y-axis, time on the x-axis, and reactant changing to the products, that is the particular reversible reaction written. Now can you see that here forward reaction, it is showing some decrease in the rate, and then after this time it is a straight line. So this is forward reaction. Why the rate will be getting low? Because generally we believe that while going from reactant to the product side, the concentration of reactant it decreases and concentration of product it increases with time. Generally in a particular chemical reaction, the reactant concentration will decrease and product concentration will increase with time. So here, when the concentration of reactant will decrease, the rate of the reaction also will get decreased in that particular direction, and that is what is happening. So it is decreasing like this way, but after some time when its equilibrium will start existing, so TQ will come, this is called equilibrium time, and after that it has become a constant concentration. So if I just extrapolate this line, can you see that this rate is constant? So this is rate versus time curve. Rate has to be same as I told you. So just check it out for the product side. Initially we believe that, okay, we have assumed that there is a zero product. So when there is a zero product, the product will start increasing, and if the product will start increasing, the rate also will get increased because the concentration will increase. So if the product is increasing, rate is increasing, rate will be also increasing up to a certain point, and after that it will become constant, and also not only constant, it will now become equal to the forward rate as well. So when we say equal to the forward rate, that is the condition of what? That is the condition of equilibrium. So forward reaction rate will be equal to the reverse reaction rate or backward reaction rate. That is the point of equilibrium. So I hope you understood. Rate has to be equal. At this point, after this time, what is going to happen? The rate of the forward and the backward has become equal. They are at the same point. They are at, say, let's say some REQ. So equilibrium is achieved, and we say that the rate of forward reaction is equal to the backward reaction rate. Now here, with rate though, we have drawn the curve and we have seen the curve that, okay, first the forward reaction is getting decreased and then it is a constant. Reverse reaction rate is getting increased and it is a constant, and it should be equal to, it should be not only constant, it should be equal to also the previous curve. But what about if I plot the curve of concentration versus time? So when we plot the concentration versus time, then one graph can be like this, definitely, because while going in that particular direction, if a straight line is coming, that means constant concentration, just like constant rate. But it is not a condition that the concentration will be equal also. So there can be many possibilities. Let me show you the curves, then I hope you will be able to understand. Like here, there is only one possibility. This line cannot be above or below, okay, these line after the TQ will be at this point only, same point. What I am trying to say is that I cannot draw it like this way. If I say the rate versus time for forward backward, I cannot say that okay, up to here it will go decrease and then it is a constant, and product will up to here increase and then it is a constant. No, this graph will be wrong. Okay, there won't be any difference between the rate point at the time of equilibrium. If this is, you are saying this is your TEQ, then a TEQ rate has to be equal. The y-axis should be pointing the same thing. So this is wrong. Similarly, if somebody he draws like this way, that okay, rate versus time, I will draw like this way, that reactant has decreased and then constant, product has increased, and this time the rate is more and it is a constant, and I will say that this is my TQ. Even this graph is also wrong. Okay. Why? Because here also the rates are up and down. Here also rates are up and down. But after TQ, the rate should be equal. That is the main point. So the rate is equal only in this curve. So only one graph of rate versus time will be drawn. Next. Next is, here you can see concentration versus time curve. So when it is a concentration versus time curve, I told you that there can be one possibility, just like the rate, that the reactant concentration will decrease, okay, product concentration will increase, right, and at the time of equilibrium what will happen, they will become constant, and they can be equal also. They can be equal, they cannot be equal, that is there, that depends upon the chemical reaction. Okay, that depends upon that how many moles we have taken, how many moles has been used in the reaction. So here what is happening in this curve, the rate of forward reaction is equal to the rate of backward reaction at this point, equilibrium is achieved, dynamic equilibrium has achieved, and also what has happened, the reactant concentration after this point has become equal to the product concentration also. R is equal to P here. But as I told you, this is a special condition for rate of reaction because they has to be equal. So we can have some more possibility of the graphs and we will check it out, those all possibilities. So if I check out the possibilities, these are another two possibilities of concentration versus time. Now here again reactant will keep on decreasing, product will keep on increasing as our general assumption, which we have assumed that reactant in a reaction will keep on decreasing by time, product will keep on increasing by time. So what will happen, that here also reactant is decreasing, product is increasing, but can you see after this TQ point, they are becoming constant but they are not equal. But then also this graph is correct because for concentration, this is your product, this is your reactant. Here what is happening, here the reactant concentration is less than the product concentration. That is how this graph is occurring after equilibrium time. So EQ we can mention. After equilibrium time, so equilibrium concentration of the product and the reactants, reactant equilibrium concentration is less than the product equilibrium concentration. Here what is happening, here again at this point my TEQ is coming, equilibrium time is coming, but you see here this is your REQ and this is your PEQ. Still it is constant, so equilibrium is existing, but you should remember that this graph is only possible when your reactant equilibrium concentration is more than the product equilibrium concentration. So when we will draw concentration versus time curve, then there are three possibilities. That can be made of the graph. One, which we just see here, concentration versus time, when the reactant and the product equilibrium concentration will be equal also. This can be also one of the case. They are constant and they are equal. And the other two possibilities are that they are constant but they are unequal, right? That is also the possibility. So in an unequal, there can be two possibilities. Either reactant will be more than the product or product will be more than the reactant. So based upon that, we can have two curves more. So in a rate versus time, we only have one curve, but in concentration versus time, we have three types of curve possible. This is what you have to keep in mind with respect to the graphs. Now let's discuss the characteristics of chemical equilibrium. So when we talk of the characteristics of chemical equilibrium, then it is like we should remember some points of the chemical equilibrium, basically. So first of all, it is written here, it can exist only in closed container. So when we are talking about the chemical equilibrium, it is generally said that in closed container it occurs. Now why it is said? It is said because suppose in a chemical reaction, a gas is formed, okay, in the product side, and if the reaction container is open, so what will happen in the open container? In open container, your backward reaction is not possible because gas will be going out of the system. If gas will be going out of the system, then it is not a backward reaction is not possible. If backward reaction is not possible, then the meaning is that the reaction is not reversible reaction. The reaction is irreversible reaction only in one direction. So if it is a irreversible reaction, how it will be giving me the equilibrium things? Okay, so the basic condition, please remember, which we have already covered, that the reversible reactions are only there for happening the chemical equilibrium process, because we need two types of the rates, forward reaction rate and the backward reaction rate. So there should be both the reactions in the particular question. So it is like if an open container is taken, then obviously if any product is gas, then it will not give me the equilibrium state. So that is why this condition is very valid. Second condition is, at equilibrium the rate of forward reaction becomes equal to the rate of backward reaction, which we have already seen that this is the basic and required condition for equilibrium to exist, because if the speed will not be same, then what will happen? If suppose A2 and B2, they are reacting more speed than the AB dissociation, then what will happen? AB will be only getting formed and A2 and B2 will be less getting formed, and in that way the equilibrium will not be existing. Always it will be like AB side slowly more concentration will get formed. Like what AB and A2 I am talking about? I am talking about this particular example which we have seen. Okay. If suppose the forward reaction rate is more, then what will happen? That A2 and B2 will slowly be getting consumed and only AB will be left much in the particular container. If AB dissociation to A2 and B2 is more, then what will happen? Then your A2 and B2 will be by time present more in the container and AB will be present less in the container. So again that will be like more towards a particular one direction only. That is not going to give me the equal rates, chemical equilibrium, because at equilibrium what do we say? We say that the concentration should become constant after some time. But if the rates will not be constant, not be equal, then obviously if one rate is more, another is less, then there will be concentration difference at every time interval. So concentration difference should not be there. There should exist some time after that. After that, the concentration should become constant. So that is what A2 and B2 I was talking about. So rate should be definitely equal to the forward rate should be equal to the backward rate. Then concentration of reactant and products become constant. That is again we have seen. Fourth is, it is called dynamic equilibrium. Now please remember here, dynamic equilibrium. Dynamic means what? Something in motion, in movement is going on. So concentration are becoming constant, I agree, But it is not the case that reaction has stopped. See, concentration can become constant then also when reaction has stopped. We are not doing any reaction. Suppose A2 is 5 mole, B2 is 3 mole and AB is 10 moles and we are not doing the reaction. Then also concentration will be constant, right? But that is not called equilibrium. That is not called the equilibrium. Equilibrium means what? Reaction is still going on, but then also the concentrations are constant. Just like that person was moving up, lift was still moving down, and then also location was not changing. That is called equilibrium state. So in here also, reactions is still going on, forward is going on, backward is going on. Reaction does not stop at the equilibrium, and that is why equilibrium is called dynamic process. So it is a dynamic equilibrium as reaction does not stop at equilibrium, only the rates become equal. Very, very important point. See, concentration, as I told you, they can be constant then also when we do not have the reaction going on. But the meaning of the chemical equilibrium is that reaction is going on, then also the concentration is not changing. I hope now you understood about the chemical equilibrium in detail, the meaning of it, every small point I tried to cover. So I hope you have got the point. And equilibrium point can be denoted by concentration, pressure and color. So concentration, whenever we say, then we encounter one equilibrium constant which is called Kc, and when we say pressure for the gases, then it is called Kp, and with color intensity also, when the color intensity is not changing much, there also we will be able to find the equilibrium state. So this is what about the meaning of chemical equilibrium we have done today. In my next session, I will be talking about the Kc, Kp and the numericals, but today we have studied the meaning of chemical equilibrium. I hope it is clear by the help of that physical lift example, and also the rate of forward and the rate of backward reaction should be same. That is in your mind, will be in your mind forever. The concentration has to be same, constant, but the rate has to be equal, same. This is what we have to remember. I hope the graphs are also very clear. Please revise it again so that you will be able to solve all the questions. And because you have here, you have attended the class, so big thank you from my side. But you have to practice a lot. In the next session, we will be talking about the calculation based thing, Kp, Kc and all, how to write, when to ignore the concentrations, and there is a condition. So everything will be try to do in the next session. That's it for today. Thank you.